Let's start with the simplest case here, where the denominator qx in our rational function r of x over q of x is a product of distinct linear factors. That is, it breaks up into a product of factors of the form ax plus b. Let's assume we have n of them. Then we can write this quotient, this rational function r of x over q of x, as a sum of partial fractions of the form a1 over the first factor, a1x plus b1, plus a2 over the second factor, a2x plus b2, etc., plus an, if there are n factors, over the nth factor, anx plus b. We're assuming here that these factors are distinct, not repeated, and we create one term in our expansion for each of the factors. The numerator is a constant, ai, and the denominator is the factor itself. And then we solve for the a values by comparing our rational function to this expansion. Best thing to do is look at an example. Suppose I want to integrate 1 over x squared minus 25. Well, now here r of x is 1 and q of x is x squared minus 25, so it's certainly a proper rational function, and x squared minus 25 breaks up into two distinct linear factors, x minus 5 and x plus 5. So to find this partial fractions decomposition, I create two terms in my partial fractions decomposition, one for each of the linear factors in the denominator. I have my rational function 1 over x squared minus 25 is equal to a over x minus 5 plus b over x plus 5. When I have a small number of factors, I can just use different letters from the alphabet for the constants. So I'm saying that 1 over x minus 5 times x plus 5 is a over x minus 5 plus b over x plus 5. And my job now is to find values for a and b and then integrate these two terms. Well, to find values for a and b, I multiply by this denominator q of x on the left-hand side of this equation and on the right-hand side. It's best to keep the factored form because then you can see how the cancellation works on the right-hand side. So multiplying the left-hand side by x minus 5 times x plus 5 and the right-hand side by x minus 5 times x plus 5, I get 1 on the left equals a times x minus 5 times x plus 5 over x minus 5 plus b times x minus 5 times x plus 5 over x plus 5. Now I cancel whatever factors I can on the right. You see in this first term the x minus 5's cancel, and in the second term the x plus 5's cancel. So all of this reduces to a single equation. 1 equals a times x plus 5 plus b times x minus 5. And remember, my goal here is to solve for the a and b because this is going to help me simplify the integral I was given. Well, there are two ways to solve for the a and b. We have a variable x on the right, so we have a polynomial. Remember, a and b are constants. And whenever two polynomials are equal, the coefficients of the powers of x must also be equal. So if the coefficient of x on the left is 0, then the coefficient of x on the right is 0. And if the constant term on the left is 1, then the constant term on the right is 1. And this helps us solve for a and b by comparing coefficients. So the first thing we do is write this polynomial on the right as a polynomial where we've gathered up the coefficient of x and we've put together the constant term. So we get 1 equals ax plus 5 times a plus bx minus 5 times b, and then gathering up the terms with x, we have 1 equals a plus b times x plus 5 times a minus b. Now comparing coefficients on the left and on the right, we have the constant coefficient on the left is 1, and the constant coefficient on the right is 5 times a minus b, so they must be equal. We must have 5 times a minus b equals 1, and the coefficient of x on the left is 0, and the coefficient of x on the right is a plus b, so we must have a plus b equals 0. Now we have two equations in two unknowns. They're not very difficult to solve. I can solve for one unknown in terms of the other and substitute in the other equation. So we have a plus b is 0. That gives me b is minus a, and then I can substitute this in my second equation, 5 times a minus b equals 1, to get 5 times a minus a, which is plus a, equals 1. So we get 10a equals 1, or a is 1 over 10. And then, of course, b is minus that, so b must be minus 1 over 10. Now we know what our partial fraction decomposition is. We have 1 over x squared minus 25 is 1 over 10 over x minus 5 minus 1 over 10 over x plus 5. And now it's pretty easy to integrate. We have the integral of 1 over x squared minus 25 is 1 over 10 times the integral of 1 over x minus 5 minus 1 over 10 times the integral of 1 over x plus 5. We can use substitutions and logarithms. So for the first integral, if I let u equal x minus 5, and for the second one, if I let w equal x plus 5, we get our integral is 1 over 10 times the natural log of the absolute value of u minus 1 over 10 times the natural log of the absolute value of w plus a constant. Then plugging back in the x values, we get that that's equal to 1 over 10 times the natural log of the absolute value of x minus 5 minus 1 over 10 times the natural log of the absolute value of x plus 5 plus a constant. And actually we can put those two terms together. Pulling out the 1 over 10, we know that the natural log of a minus the natural log of b is the natural log of a over b. So our integral becomes 1 over 10 times the natural log of the absolute value of x minus 5 over the absolute value of x plus 5 plus a constant. Now let's scroll back just a little bit to where we solved for the a and b, because there is another method here which we could use. We would like to solve for the a and b, which make 1 equals a times x plus 5 plus b times x minus 5. Now, one thing we can do is select values of x, because this equation must be true for all values of x. So I could plug in selected values for x here to get new equations relating a and b. So for example, if I plug in x equals 5 here, this second term disappears. And I get 1 equals a times 5 plus 5, which is a times 10. And straight off the bat, I have a equals 1 over 10. And I could plug in x equals minus 5 here, and the first term would disappear. And I would get 1 equals b times minus 10, or b equals minus 1 over 10. So you have options on how you solve for a and b here, and sometimes you can find the values of some of these constants by some fairly obvious substitution.